Hello friends, welcome back. In today's session, we'll be looking at how to derive an expression for strain energy due to shear force, due to the applied torque, and due to the applied bending moment. Right. So we'll be going through three derivations in today's session. Let me begin with the first one. These are small derivations. Hardly it takes around 15 to 20 minutes. So please concentrate. So in the first case, when I say expression for strain energy due to shear force. Okay, what I'll do here, I'll be taking a particular element, I'll be finding out the strain energy for that element, then I'll integrate it for the entire length of the element in order to get the total strain energy. Right, so let me consider an element. Okay, so let me consider a rectangular element, right? And let us say then on this force or on this surface, I'm going to apply certain shear force. I'm going to apply certain shear force, say F, along the vertical surface. So क्या होगा if you just keep this as a fixed one, right? If you are keeping this as a fixed, and then the new shape or the deformed shape of the element will be as shown in the green colored ink, right? So here the strain obtained is d theta. Now this vertical displacement or the transverse displacement here, I'll take this as dy because it is in y direction, right? And since I have considered an element, since this is the element, the length of the element here in this case, I'll take it as dx. I'll take it as dx. Okay, so I'll just write here, consider an element of length dx subjected to a shear force F as shown in the figure. Right. So once if you consider this, after applying the shear force, the vertical displacement or the transverse displacement is found to be how much? It is dy, and the strain here is shear strain is found to be d theta. Right. Now what I'll be doing here is strain energy stored in the element is given by the strain energy stored in the element is given by, so since it is element, I'll take it as delta u. So it is 1 by 2 into F into dy. Right. Now try to understand how I have taken this. We just correlate this with the previous thing what I have derived for expression for strain energy for axial loaded member. So in that derivation, I have showed you how u is equal to 1 by 2 into deformation into force, right? 1 by 2 into deformation into force. I have taken that because it gives me the area under the load deflection curve, right? So you should not have a doubt at how I have taken this expression. If you are having that doubt, I request you to go to the previous derivation where I have derived an expression for an axial member subjected to an axial force, right? So from that I have taken this equation. Here it is dy, displacement is dy. Next, so therefore delta u is equal to, now as usual I'll be going for some substitutions. So what all things I am substituting, I'll just write it here onto the left hand side. So it is 1 by 2 into F into, now here in this upper triangle Let us say it is like this. Right, so this is dy, this is d theta, and this is dx. Right, so for this triangle, now here in this triangle, tan of d theta is equal to opposite divided by adjacent, so it is dy divided by dx. Right, now we know that for small angles tan of d theta is nearly equal to d theta. Right, for small angles tan of d theta is nearly equal to d theta. So I'll slightly extend this line. Now what is next thing? So therefore d theta is equal to dy by dx. So this implies that I want to substitute for dy. So this implies that dy is equal to d theta into dx. So this is important. So here where there is dy, there you put the expression as d theta into dx. D theta into dx. Right? Now we know that modulus of rigidity modulus of rigidity, it is G, is shear stress tau divided by shear strain. In this case it is d theta. Right? So therefore I'll just exchange this, cross multiply this. D theta is equal to tau divided by G. Further, what I can write, d theta is equal to, I have exchanged these two things. So d theta is equal to tau is force divided by area into G. So I'll write here tau is equal to force divided by area. Right? So that force divided by area, you put it here, you'll be getting an expression for d theta. This you take it as your equation number 1. So therefore equation 1 becomes, what does equation 1 become? Delta u is equal to 1 by 2 into f into d theta is f divided by a into g into dx. So therefore delta u is equal to 1 by 2 f square divided by ag into dx. So this is for element, right? So if you just integrate it for the entire length, then we'll be getting this total strain energy stored in a particular member because of shear force. So I need to integrate it on both the sides. So integrating it on both sides, we get del u is equal to integration of 1 by 2 f square divided by ag into dx. So this should be integrated for the entire length. Right? So what you'll be getting here, you'll be getting expression for strain energy, which is f square divided by 2ag into dx. So this should be integrated for the entire length 0 to L. Right? If you just put it, then what I'll be getting, f square divided by 2ag, everything is constant. Integration of dx is x, so it will be f square L divided by 2 times ag. Right, so this is the expression for shear strain energy. This is the expression for strain energy due to shear stress, or this is the expression for shear strain energy. Right? So next we'll be going for the second derivation. Next we'll be going for an expression for strain energy due to bending. Right, so in order to derive that, I'll be considering a beam which is subjected to a bending moment. Let us say I have a beam. Let us say the length of the beam is L, and this beam is subjected to a bending moment on either side. Right. Now, in order to derive things initially, I'll be considering an element in this beam. Say its length is dx. Right. Consider an element in the beam whose length is dx. I'll just write here. Consider a beam subjected to bending moment m on either side. Either side. Initially, to proceed with, consider an elemental portion of the beam, portion of the beam whose length is dx. Right, so let me say I have considered this much distance, right, and this distance is dx. So I'll just take this part out and I'll just redraw here. So I'll write here as element diagram. Element diagram. Right. So since it was in red color, let me draw it using red color itself. So when you are applying this bending moment, then this will be something like this. Right. So I have just drawn the exaggerated view of this element. Okay. So here this portion is dx. Right. And if you just check here, this is the part which I have redrawn. If you just extend this, right, same thing on this side. Right, so what you'll be getting here, will be getting a point, we call it as center of curvature, and we know that this distance will be equal to r. So up to here this point is r. What is this? This is nothing but neutral axis. Let's write here it is neutral axis. So this distance here, we already studied that, so I'm just repeating this. So this distance is r, right, and this distance is dx, and here this angle, I'll take it as d theta. Right, now I'll be writing everything with respect to this because this is my element diagram. Strain energy in the element is given by strain energy in the element is equal to, so the same thing what I had taken previously, it is delta u, how you write it is 1 by 2 into the force which is causing, in this case it is not the force, it is the bending moment which is causing this to bend. It is subjected to a bending moment of m. So instead of writing the force F, what you can write here is m into the distortion or the deflection what it is causing. Here it is angular deflection, so it is d theta. All these things I am writing it on a similar lines of the expression what I derived for an axial member subjected to an axial load. There I had shown you how I got an expression for strain energy. All these things are on similar lines, right? So here I'll be substituting few things, you just note down. So we know that from our trigonometric knowledge of what we have studied in your PUC and our engineering mathematics knowledge. So for this kind of an arrangement, sector arrangement, L is equal to R theta. From the element diagram, from the element diagram, what I can write, L is equal to R theta. So length of the arc in this case is dx is equal to R into d theta, R into d theta. I want to substitute for d theta. So therefore d theta is equal to dx divided by r. D theta is equal to dx divided by r. Now also we know that from the flexural formula, right here, from flexural formula, so what I know that sigma b by y is equal to m by I is equal to E by R. Okay, now I'll be taking or combining these two. I'm just interested in these two, right? So you just club these two. From these two, I'm going to take the value of 1 by R. So therefore 1 by R is equal to m divided by E into I. 1 by R is equal to m divided by E into I. So we know that d theta is equal to dx by r, d theta is equal to dx by r, right? So that can be written as, so it is 1 by r, here you are having 1 by r, so it is dx into m divided by E into I, right? Now this is the expression for d theta. Therefore strain energy stored in the element, strain energy stored in the element, so that is delta u is equal to, so what you get, it is 1 by 2 into m, 1 by 2 into m into d theta. D theta value is m divided by E into I into dx. So therefore delta u is equal to m square divided by 2 times EI into dx, right? Now this is for an element, therefore integrating on both sides, integrating on both sides, we get, so if you integrate on both sides, I'll be getting u is equal to integration of 0 to L m square divided by 2 times EI into dx, right? So this is the expression for, strain energy due to bending, strain energy due to bending. So further you can write one more step, delta u, so it is m square divided by 2 times EI, integration of dx is how much, x, for that it is 0 to L. So delta u, if you integrate, it becomes u is equal to m square L divided by 2 times EI. Right, so this is the expression for strain energy due to bending. Right, so that's it for today's session. Have a great day. Take care. Bye bye.